In example 1.2, we're going to be looking at infinite sets again, but this time we're going to be looking at infinite sets that are represented using interval notation. So with the interval notation, the best way for us to understand what exactly the sets look like is to take a look at how they appear on the real number line. So for part A, we have a set here given by -5, 4. So I want to draw a number line, and this might be the most time-consuming part of this example, is going through and drawing your number line and putting tick marks. So we'll call this 0. To the right, we always put our positive values. To the left, we'll put in our negative. So it looks something like this. Of course, we can't represent the entire number line. We just represent an excerpt of the number line that will be large enough for us to represent the set that's in question. So our set here, again, starts at -5 on the left and +4 on the right. These are known as a bounded set. So on the left, my boundary is -5. Now, I put an open circle here because this parenthesis means that I'm not supposed to include -5 as part of this set. So this is known as a open symbol. Whereas on the right boundary, the right side of this this set is going to have a square bracket. Now the square bracket is known as the closed symbol. So when I come over here to +4, I'm going to be sure to put a closed dot there at 4. And what the interval notation allows us to do is represent all of the real numbers that are in between the boundaries. Everything from -5 all the way to 4. But -5 is not included in this set, while +4 is included in this set. Let's look at another one. We have 2 to 7 halves. So a number line, probably not as large as the last one, needs to be drawn. And on the left, I'm going to start at 0. And moving to the right, I'm just going to put positives all the way up to 5. And my left bound is 2, which is open circle at 2. The right bound, which is represented as a rational number, 7/2, in fraction form. Think of it in decimal form, and it's going to be 3.5, which will also be open. But again, the interval notation describes that we want all of the real numbers in between the boundaries and not including the values that are at the boundary themselves. So this set does not include 2, and this set does not include 3.5. But any number that you can think of in between 2 and 3.5 is included. Let's take a look at part C, 0 to pi. Let me slide this over a bit. And again, I won't need a huge number line for this one. So on this one, we have a closed boundary on both the left and the right. So I'll put a closed dot at 0. I'll put a closed dot at pi, which is approximately 3.14. So it's just your best guess at about where that is. And then we will make sure that we indicate that we want all the real numbers in between. And that's what we get for part C. So coming over to part D, we have a combination of closed and open, just like we did with part A. So let me draw my number line. And the more practice you get, the better you will be at drawing your number lines, more efficient, more quick. Starting at -1 here, we have a closed dot. +3, we will have a open, and we'll take everything in between. So these 4 examples are all examples of bounded sets. They are infinite because there is an infinite number of real numbers that we could select in between the boundaries. On the next couple of examples, part E and part F, they are not going to be bounded on both sides. So when you look at part E, you can see here that there is a negative infinity symbol on the left, but there's a +2 on the right. So this negative infinity right here, I want to make sure that we're very clear on this. Negative infinity is not a real number. The purpose of that negative infinity is to help represent that this set is unbounded, and it tells us specifically which direction it is not bounded. It is not bounded on the left side. Whereas on part F, we do have a boundary on the left side, but on the right-hand side, we don't have a boundary. So again, the purpose of this infinity symbol is not to represent a real number, but it is there to represent that this set is unbounded going to the right. So let's see what these sets look like on the number line. Part E, I will put a open boundary at 2, but that's supposed to represent the right boundary, and there is not supposed to be a left boundary. I'm supposed to be heading in the direction of negative infinity. So when I start drawing my line, I'm going to go from my open boundary at 2 to the left, and to represent that it never stops doing that, I put an arrow, and this is how we illustrate the interval from negative infinity to 2. So that same idea will apply for part F. Let me draw a number line, and this time I'll start over here at 0. And that should be good enough there. And I have a closed boundary at 4. So I'll put a closed circle there at 4. And the right boundary, represented by the infinity here, is, well, there is no right boundary. It's going to continue on forever. It's unbounded in that direction. So as I start from 4, I'm going to continue on to the right, and I should do so forever, and so the arrow there represents that. So all these examples were examples of infinite sets that were not your natural number, real number, rational number, or the integer set.